thought I was talking. Sorry, it turns out I was muted. So hello, is the screen readable?
If you could make it a little larger, that might be helpful. But yes, we can see it. We can read it.
Making it a little larger might be a bit difficult now because I have to recompile the font.
No worries. On with the show.
Okay, great. Thanks.
It's fine as it is.
Great, thanks. So, hello everybody. My name is Onat, and I've been working on this language for the last decade. And what you're looking at is a block-based for. I mean, I'm not actually really good at presentations, and I haven't really prepared for the talk. So excuse if the talk is like a little bit anyway, a train wreck. But let's see what happens. So the thing is, this is actually like a Fort editor that's encoded in another Fort editor that looked like hold on. That looked like this. So this is the previous version of that editor, and this is a text-based Fort. So you can just type anywhere on the screen. This is like just 4K blocks per screen, 64 by 64. And text-based Fort takes about 60 milliseconds to compile the editor, which you're looking at here. So that's number that you're seeing here. That's like 17.8 milliseconds. That's the text-based performance, like when you're processing text to compile. And this takes 8.24 milliseconds for two platforms, Windows and Linux. And I can say like, okay, yeah, it takes 4 milliseconds per platform, as you can see here, if I don't compile for Windows, and 8.2 milliseconds. For the entire program, that looks like this. So this is VAMP, and this is the first series program that I've coded in Fort that's like, beyond a certain complexity that, like, okay, this editor that we were looking at was manageable in text-based Fort, but to do this in text would have been much more difficult for a lot of reasons that we're going to get into. And yeah, this is based on a binary encoding, which is why this is so fast. And it gets translated directly into machine code. So yeah, let's start with like why Fort is actually not, I mean, Fort does a lot of stuff right, but it's actually still, I'm going to critique it as a runtime opinionated language. And that means the language is has a defined runtime, which is, in the case of Fort, it's a data stack and a return stack, right? And anything that you could configure per your own Fort, of course. I like to have global memory, for instance. So the thing is, how do you run a Fort on a GPU, right? Because like this program that we're looking here, it also has like shaders, and like it's actually just compute shaders and rendering text like this. And running Fort on the GPU in the traditional sense is kind of like impossible, because you have to maintain that stack with registers, and it's not that it's not that good. Versus like because I mean I've been programming this for 10 years, more than 10 years actually, and the thing is, it had to be the most performant language ever also, and the Fort overhead, just by this example, the 16 milliseconds versus like 4 milliseconds. That's like 4x difference between using data stack versus using registers only, right? So this fort is like the stack is just 2. There's only 2 items on the stack. So and you can see the stack is visible on the top left corner here. So you can go anywhere in code and say, okay, what does the stack look like here? Or here, for instance, that's like all the instances that this definition is being called from, the stack is visualized. But why do we need stacks, right? Stacks are there so that we can pass information in a convenient way. Otherwise, we would have to use variables, and having to name variables all the time is a lot of bookkeeping that you have to do versus just using stacks, right? And let's see. I mean, this is instead of using stacks, we can just use global memory. For instance, we don't have to use stacks even at the runtime, but I use stacks at the compile time because it makes passing arguments a lot easier. Sorry, I'm just scrolling through the code to find like an interesting place, but because this subject is actually like maybe we should just stay on the screen for a while. I because this is like the first screen of this environment, and there's a bunch of numbers here and like a structure here. So in an old fort I made, there was this like begin and end definitions, like begin definition and end definition like that, versus this means the beginning of the definition and end of the previous definition, right? So you don't have to remember to close your words, right? Each definition closes itself, or if there's no definition, if there's just space, then that means that's an execution, which we're gonna get also, later. So actually, this is the perfect place to mention execution. So I think we have to code in the simplest way, and I don't think it involves a lot of abstractions, right? So I think we should just code everything in assembly, including the language and the editor itself. And how do we write that assembly is, of course, we don't have to write it like, we don't have to write it instruction by instruction. We can use a macro language like this for it to implement that other Fort core if we wanted to, or other language extensions if we wanted to. Because that's the other point, right? Like it has to be a foundational language that's that can last forever, because it's the simplest that it gets. And the design space for that is like 2 registers is, I think, the optimal point, because if you have 4 registers, that's a lot of shuffling, and most operations are like they just use 2 operands. So 2 registers for stack size at compile time is enough for a program of this complexity. Oh yeah, I could just open this, of course, for like the And this program is, so I can basically tile the screen any way I want. And it does not use stacks at all. Like, I mean, it uses stacks at some places, but not in the way that you would think. Like, you know, there is no like the stack overhead of like, you know, traditional Fort. It's all compiled down to assembly because, in a way, it's all programmed in assembly. But you know, the assembly is high-level macro Fort style, and I got basically anywhere anywhere I have like, oh, okay, there we go. I have like exact assembly output that I'm interested in for the architecture that I'm compiling to. So this is x64 for now, but you could compile to ARM64 or any of the microcontrollers or whatever. You could use any computer to transpile to any other computer. So as long as you can communicate with that other computer via like sending the compiled code that you just wrote, I mean, that you just generated via execution, which is like the, yeah, the subject that I wanted to get to is like, we don't have to think code as like some complicated, you know, like structure. It's just pure execution that generates a very simple, that maps to very simple assembly, and then you execute that code so you have exact definitions and simple definitions, and the execution is also very efficient. And so
a question about your screen is the color is highlighting, or is there some encoding for the coloring?
oh yeah, there's semantics associated with color. It's like color fort, but you know, it's compile time color fort. Like, I mean, color fort is, as far as I know, it's still text encoding based, which is still valid, by the way. It's like, it's just slower and it has some disadvantages also, but you might want to do text based color fort instead of like this index-based color fort. So the index-based part is there's a dictionary that maps each word to, you know, each of those words is like, I mean, I could just go to this loop and I could call this like loop, for instance, and it will change everywhere because it's like,
I see. So you're storing a central index for each word in the. I see. Interesting.
exactly, and they're
how big are each is each word? Like, how big is the index space?
well, there's 24-bit indices because I want to pack each instruction to 4 bytes. So 24 bits of that 4 bytes is dedicated to that. But in the next iteration, actually, I'm going to do 4 bytes for indices, and then I'm going to store 1 byte tag in a separate block. So you have like, I mean, this is going to get faster. You know, this is just baseline.
I see. So it's an index and then a tag. Got it. Thanks.
Yes, exactly. And because if you don't have that index, that means you're hashing, and then you have to do that hash lookup, which gives you like dynamic local context. But I like global context more than local context because I have exact mappings, you know, exact semantics, instead of like, oh, maybe I called this word in a different context, so that word has like a different, that word maps to a different cell, like different index. It's like, you know, that kind of like problems I don't want to have to deal with, like with text-based, but like still text-based is valid in certain contexts. Like maybe you want to do, I don't know, maybe you want to do like free-form programming without having to require a complex editor, because instead of like having the complexity of text in the language, you've embedded that complexity in the editor, because you know, when you're writing, you're like looking up this you know, word like loop, for instance, and that's I'm pulling from this concept that I call the deck. So I have like a deck of cards, and I have a bunch of words that are like, these are my Vulkan words, for instance, and these are FFmpeg words when I'm like dealing with FFmpeg, and like a lot of the words now I put in a to-do list to implement later, and I just never got around to it, and it's not even like a problem. And this is just one encoding, right? This is not central to the execution. This is just for printing. This is not the core language. So in the future, if you're like doing open source, for instance, you have the option to say like, just ship the source, but not the symbols, not this like dictionary part. So in a sense, you still have the source and the numbers, and you know, but you can still protect your IP in like, you know, symbols, for instance, for like, I don't know. And there is also the possibility of embedding this whole thing into the program itself. So the core language is 2 to 4 kilobytes. It's actually should be 2 kilobytes. I haven't checked recently, but yeah, it's very simple, because what I'm doing is I'm just looking like I'm just generating a template-based like code, so that I can execute it efficiently instead of like having to incur the interpreter cost, right? So I mean, that's like also happening in this text-based language, and that's why it's 16 milliseconds. I mean, it's still fast, but you know, having to hash and having to look up that overhead is like easily like, yeah, easily yeah, 12 milliseconds of cost.
How
Right?
how do you manage the index space? Like that's the main thing that's kept me from going down that road, is sort of like, is there a lot of complexity in managing?
Yeah, that was that grew to be a problem, because like after a while there's just a lot of words, and like so I solved that via like tags. So I have these 16 word scrolls, and I can paint them with tags, and then I can select tags over here via the deck. So each of those are like tags. I mean, it's kind of complex. I'm not going to do 4 tags in the next iteration. I'm going to do just 16-bit index plus some predefined tags instead, like API, implementation, you know, that sort of thing. Like, you know, this is not the end iteration. I mean, there is a lot of UX improvements to be, you know, to be imagined, right? There's to be explored. I mean, that's very exciting about this language, is like it's also going to run on Steam Deck, and also VR, and also phones and tablets, right? Because why not? We're not like constrained to the keyboard anymore. It's just like picking up symbols. I mean, you could essentially draw on the screen instead of like typing on the keyboard. And you said like, how do you manage? I mean, you can just type words like, you know, let's say A B C D E F. I mean, you could just like define words like this. You can move them around, you know.
And then when you insert them into the source space, then you have to use the selection on the left, or you can you do the lookup at that point to.
Yeah, I mean, you can actually. I mean, you used to be able. I mean, I used to be. I used to just have this dictionary space, and now I just type something, and if I need like something like index, for instance, index for something, I just press Control Space, and that gets redefined wherever it gets redefined, which is like configurable. Like, you know, I want to define index ABC here, for instance, and then it gets defined here.
You're kind of consciously managing the index space as you place add new things, and I see.
Yeah. I mean, it's like you can move stuff around, and the only thing that you have to do is like walk through the whole source and patch, you know, numbers. it's simple. I mean, the editor is also very simple, which is important if you want to import the editor for open source programs. Like, you don't have to install 4 GB of Visual Studio, like 200 megabytes of PHP or whatever. It's just 64 kilobytes of editor, if even that. Like, and it's portable to anywhere because it's so simple. So yeah, there's a lot of stuff here that makes programming easier, which you can see as structure in the code, like a new syntax for like conditionals and loops, and like this loop, for instance, how it's implemented is like I can jump. I got like jump the definition, right? So what this loop does is like it increments depth by 1. And whatever depth is, like, it's usually zeros, as you can see over here. It's like, and then you +1 that, and then you see like, oh, it's +1. I mean, you can just see all the code flowing at compile time, right? And that's the stack over here. And what's interesting about this, like, another interesting thing about this language is like you should be also able to see the data flow as it's happening at runtime, right? So that's also possible with this language. So I'm just like iterating through like, okay, what was with play, for instance, that's set up here. When I click previous, for instance, I want to record like this with play index, right? So, and that shows up over here just by this corner. So that's like 68, for instance, or we could say, okay, let's for instance run this and then like press like previous or next 3-4 times. I think I pressed 5, 6. Okay, let's count it. How many times we pressed? So okay, so let's see. 1, 2, 3, 4, 5, 6, 7. Okay, we pressed 7 times, and you can see like the data flow as it's happening through runtime. And this is the most basic form. You could imagine like moving over the mouse and seeing the full data flow, which I'm going to implement for the next editor and so on. But it works, and you can even embed more metadata there. And I mean, this is essentially free printf. Like you don't even have to type printf. You just say like, okay, what was like hot slot as like this code was running. And if I'm like creating some stuff, then I'm gonna, yeah. So the hot slot was like 3D, for instance, instead of like, or 31, 3D, 3D. It's like, it's when you're debugging, it's instant visualization, which is all you need essentially for fast debugging.
So for the indexes into some sort of like a name table. How is that built? Like, is it a fixed sized space for the names, or how do you manage that piece of it?
Oh yeah, that's 8 bytes per like cell. I mean, I call them cells. Like they have indices, right? But they're essentially like compile time cells, right? And you're just defining names here. You can treat them as memory essentially, and they're 8 bytes per cell.
Got it. And when
8 bytes per name also. But the name you could make like 16 bytes if you want, and it doesn't have to. But the definition of the language says that each cell is going to be 8 bytes per, like because that's the one that I think that makes sense because. I mean, you could put in type information into 8 bytes if you take care of it in many ways. I mean, you don't need 16 bytes, I think, but 16-byte names, I mean, sure, maybe if you want to.
And is the let's see, when you what about for like comments? How do you
Right. So comments are so there's 24 bits of data per instruction on this iteration, so it's 3 characters. So I can just write comments like this. They're essentially like strings, you know. They're just like encoding the string in the byte instead of like using like an external string table.
I see. So those are stored direct instead.
Right.
Yeah, I see. Because you don't want to pollute your dictionary space with. I see.
Yeah. I mean, you could store it in the dictionary also if you want, or you could pull it externally. I mean, this language is free form. It's implemented in assembly, so whatever you want to do, you're free. I mean, and it doesn't have to like. I mean, I see like, you know, I didn't want the language to be like rigid like all the other languages out there. Like Rust, for instance, is a very rigid language that says like, okay, you know what, this is the language, and like you have to fill out these tax forms, and these are the rules, and if you don't abide, we don't even compile your code or whatever. Like it's versus you're free to do whatever you want, and you know, it's like there's so little abstractions that you can implement your own abstractions or like your own extensions if you want. I mean, it's like, yeah, it's super simple compared to like all those runtime opinionated languages that are like that have to cater to all kinds of concerns, right? Versus defining like a simple language that can still solve all those problems by being flexible enough, by thinking about the output instead of like, you know, being dogmatic about the runtime, right? So yeah, I mean, there is, let's see. There's a lot to talk about for like, you know, how to program in assembly, and I mean, how to like program in assembly efficiently, right?
Assembly for what?
For, well, that's
What processor are you on?
x64 for this iteration, but that's actually like a great question. I mean, assembly for what is like, it could be ARM64 also, and the portability is one of the you know, concerns in this like style is like you know, each of like all of this is like programmed in x64 assembly, but through these high-level words. So I could replace those high-level words for ARM64 or Commodore 64 if I had to, and emulate somehow. On Commodore 64, I'd have to emulate the registers through dedicated memory. On ARM64, you have so much registers that emulating is not a problem, and you're still like, you know, within that register budget, so you're still as fast as like, you know, as if you had like all those registers. It's like it doesn't really cost you to not use registers, right?
So are you wanting to release this to others, or?
Sure. I mean, at some, like, I think I'm gonna start a stream soon where I'm gonna build this language again, and this editor again for all kinds of like different stuff like Steam Deck and VR and, you know, desktop, of course, and tablets too. So yeah, this is like, you know, it's not ready for prime time. There's a lot of like UX improvements to be made to this whole thing. Is like, you know, the situation, but as also like a proof of concept for like how fast you could compile and how fast you could run. I mean, and also how expressive it is, and how debuggable it is, how scalable it is, right? This is like a very, I mean, it takes about 1,000 times more times to compile this program in C than in this language. So, and also it's more code in C, even though C has like all those pre-compiled headers for Vulkan, FFMPEG, and so on. Because this is a, for instance, I'm just gonna say like, this is a macro language, so I can say I can just have like say 29 device to say VK device, which means like, okay, what does it mean? It means get swap chain images, which gives you the images for the for the swap chain. So in C, I would have to write this as like VK get image swap chain, get swap chain images, KYRA, etc., etc. And then I would have to say like GPU, because like it's not global, and then device versus just just device. I mean, the difference in usability and also readability is huge compared to like all those other languages that are bound by having to be text-based, right, instead of like execution-based. This
have you started making a manual or documentation?
Well, the documentation will be the streams that I'm going to do as I build the language and the editor. That's the documentation that's going to be happening. It's going to be happening live, and it doesn't even need that much documentation. The whole thing is so simple. So the thing is, okay, let's get to the language semantics, right? So we said like, oops, there's a bug that sometimes crashes the editor when I go to the top. Like, it's a stupid thing, but sometimes it happens. I haven't had motivation to fix it. So anyway, oh yeah, there it happened again. Funny. I think I'm not doing like bounds checking, which is like happens when you're programming in assembly. Sometimes you forget to do bounds checking out somewhere after some subtracting or whatever, which is again, dependent on how you program assembly, right? So, okay, let's read this. So this means define, right? So I'm defining like call, for instance.
I seem to have lost your screen there.
Oh, okay.
You still sharing?
Oh yeah, I think it's okay.
There it goes.
It's back, right? Okay, cool. Thanks, thanks for reminding. I mean, I thought we were sharing screens still, but yeah. So, oh, okay. I think I know what happened there. It crashes, and then I quit, and then that closes the share. So after
if you share the whole screen, then it'll stick. But if you share just the one window, then when that window goes away, it will.
Yeah. So call is like FFE0. So what is FFE0, right? Let's see. XX FFE0. Oops. Oh yeah, I see FFE0. That's jump to racks, right? So call becomes jump to racks because there's already a return address on the stack. So I don't want to call. I just want to jump to the top of the stack like that I want to call. So it means that we're passing at every word, the top of the stack is going to be racks, right? And the second item on the stack is going to be RDX. So out at looks like 4892. So that's like exchange RDX racks. So that's a trick actually that occurs everywhere in this code generation. Before I start the definition, I say exchange racks RDX. So depending on which one you're calling, which depending on whether RDX is on top of the stack or whether racks is on top of the stack, you call just before or just after exchange RDX racks. So that means that each calls are just single instructions instead of requiring a potential exchange instruction to align the racks and RDX for top of stack, right? So yeah, all of this is like extremely efficient, and yeah, I mean, this is also like in the definition of the language, right? And all of this is like public domain, by the way. I'm not gonna like encumber this like with patents, and I ask you not to also. Like, this is just pure foundational stuff released to like public domain for like public knowledge. I mean, as far as I know, this is like the most fundamental way of like writing in a JIT style assembly, because yeah, every instruction just compiles to a single instruction, right? Like this load, for instance, these green words are like just load from this cell index into racks or RDX, depending on whether racks is on top of stack or RDX is on top of stack. So yeah. Does that make sense in terms of like semantics, language semantics?
I'm a little fuzzy on so you're saying you have a 2-element stack that you're alternating, or maybe I'm not understanding if you could go through the register, how you're using each register, that'd be helpful.
Yeah. So racks and RDX are used for it's the stack registers, and
like top of stack and a stack pointer, or some other arrangement?
Oh no, they're just those two stack items. There's only two items on the stack.
Got it.
And this compiles move racks 256, and this compiles move RDX 512, and this compiles move racks 1024. And when it's like when you read this, then this becomes top of stack, and then you can do another write into like cell 10, for example, or whatever, and that's, I mean, it works. It's just you can do this by just using one bit. Actually, is our racks on top of stack or not? That's the one bit that you're interested in. Like, it's super efficient. So yeah.
So, sorry, still not quite following it. You're saying that so you're keeping a single bit to keep track of whether racks or RDX is the top of stack. Is that?
Yes. Yes.
So then you've got a 2-element stack, basically. Is it?
Yes. Exactly.
Got it. Okay.
Yeah. I mean, 2-element stack, because 4 elements gets very yeah. I mean, if you're calling with 4 elements, you have to deal with a lot of permutations to align the stack layout, as you expected. Or maybe you could run like 2 parallel stacks, but I don't see the point. It just makes everything so much more complex than like just having 2 items. And most of the time, I mean, two items is just enough for all the things that you might want to express with this language. And if you need more than 2 items, then you write it into a variable, and then you read it when you need it. Like, for example, there's like this free list definition, right? Oops. Let's see. I think I'm using free list, for example. Oh, there it is. So the free list, for example, uses this variable called stride, which is stride in shifts, you know. So you have to define it before you call this word. And other than that, it takes like, okay, how much free list items that I'm going to have, and that's like 32 kilobytes for directory entries, for example. And then like free list I define as like, I'm going to read into the max, like I'm going to read top of stack onto max, right, which is this 32 kilobytes, and then into base, which is this directory entries. And then I generate code like for allocation, free, previous, index, and append. So that's like 5 items that I don't have to pass on top of stack, that I can read anytime, you know, if I care to, you know. I don't even have to like deal with it. It's just there if I care to. Like, I might care about allocation of free, but maybe not other stuff or whatever for a particular free list, for example.
And it would be helpful if you could go through the tags that you're using, because that's also challenging.
Oh yeah, sorry. Yeah, that's like, so green is load and red is store. So I'm loading previous onto like, or say I'm loading the allocation function on top of stack, and then I'm writing that to plus tab, which allocates like a tab, for instance, right? Which are like, you know, which happens when you roll a new tab, like, you know, like this. It allocates like a new tab. And we can like verify that when this runs by like saying like, okay, you know what? Let's look at those variables and see what happens if I allocate 1, 2, and 3 tabs. And, you know, yeah, you got like 3 times the, and CX is like 1, DX is 5, and, you know, et cetera, et cetera. So, yeah.
What about the other? So red is read and green is write. What are the other?
Oh yeah, sorry. So write is call. So call means that you compile a call instruction literally at JIT time though. So whatever address that you had inside grow, like, you know, which is like 8 bytes, which you can jump to the definition, right? So this address gets compiled in the instruction stream in here. When you're calling.
And the pipe in front of the definition. So magenta is definition. Is the pipe just styling, or is that?
So that also gets compiled, you know, that's the definition beginning. So that gets compiled to a return, because it needs to return from the previous instruction, which is setup, you know, I mean, the previous definition, which is setup. And then there's exchange rags RDX. And then, you know, that's the definition beginning, right? So, and then you compile these, you JIT these other instructions one by one. So this is a compile, this is a load, this is a number, like this is a call, and like numbers, and this is this compiles.
And
like,
and sorry, the number. So the numbers, is there a single? The numbers are, the cyan numbers are compile of the number, or some other. Sorry, they're compile a move into racks or RDX, depending on who's top of stack.
Oh yeah, I mean, for example, this stuff, they generate nothing at the output, right? But when they get compiled, this gets translated to move racks 4, move RDX 1024, and move racks 32. And then this is like puts CX, which is defined here. You know, it's just some number that's like 1003, which is like the type, and then like the register, which is 1, you know, and then
Sorry, the
that's
yellow.
like,
The yellow is what again?
oh, the yellow is runtime.
Okay.
So that's like runtime store. So
Okay.
that generates a move RCX 020 if you can, like, you know.
And is there a runtime read? Is that the blue or no?
Sorry, can you repeat that?
Well, so yellow is runtime write. What's the run? Is there a runtime read?
Oh yeah, runtime read is CX dot, like the dot syntax, or you could just say CX at, you know, it says like move rags to RDX, move rags to RCX, like, or you could say move RDX RCX if you want, like CX at D, you know.
Sorry, I said run. I meant at sorry. Yellow is execute time read, or is it's compile time read? I'm getting them mixed up. I'm sorry.
No,
It'd be
fine.
helpful if you could go through each tag one by one, so that we.
Yes. Sorry about that, because, like, you know, it can be a bit confusing. I just got used to it, like, you know, the way it looks. The red ones, these are like calls, right? The white ones are calls, and they are compile time calls, and the red ones are compile time writes.
Okay.
And green ones are compile time reads, and yellow ones are execution, or rather like runtime. You know, so this is indexing. So each directory path is like 256 characters, for instance, and I'm indexing directory paths, which I've defined here as like maxers, which is
Sorry, the yellow is execute time read. Is that right, or execute time invocation call?
Yellow is used for a bunch of stuff. I mean, sometimes it's there's also a prefix like this equals here, you know.
Mm-hmm.
So, or this dot here, or postfix when it's a load, or
Okay.
it's a prefix.
I see. So you're okay. You've got the color. The color is overloaded. Is that all different tags, or is that?
Yes, they're all different.
Okay, got it.
Yes.
Got it. Okay, so you've got several things that are yellow that depend on the.
Yes. Sorry about that.
Ran out of colors. Okay.
Yes. When it's like yellow, then if there's like nothing, then that's a like runtime call, you know. So if it's like a so there was like plus tab that, oh, there's also like undo for, by the way, because you really need undo if you're like doing like a custom editor, right?
Yeah.
So
why didn't you use the? I'm surprised that you use color for compile time read and write, but then you use different prefixes and suffixes for execute time.
yeah, because I mean, execute time code, like, you know, has to kind of stick out, you know, because I want to see at a glance which pieces of code are generating code versus like which are like, you know, I mean, these are all generating code at some point, right? Oh, sorry, I was doing some Steam integration yesterday, so that's like undo.
And you haven't. Let's see. So you haven't explained the blue yet.
Sorry?
You haven't explained blue yet. What's blue?
Oh, the blue is comments. The blue is comments.
Blue is
it's just comments.
Got it.
Yeah.
Got it. Okay.
Like and the orange reds are strings, right? So comments and strings can be converted, you know. So this would be like a string, but it's not a runtime string because I cannot assume anything about the runtime. This is a pure compile time language that you can use to implement any kind of logic to implement whatever you need to generate for at the runtime. Like, so it's omniflexible, right? Like you can just say like, I mean, this won't generate anything at all, like no assembly. You can just, you know, be irresponsible on the stack, and like it won't matter. Like you can just, you know, let's
And
see.
what are the hard brackets?
Oh yeah, the hard brackets are the notation that I have for managing basic blocks, as I call them. I mean, they're also like terminology, but yeah. So the basic blocks are defined here, and they're like they define ranges of code that's like that you can have, like, you know, a beginning and a link and a end jump targets for. So yeah. So with this notation, you don't need ifs anymore, because you can have an if like conditional anywhere, right? So let's see a place where say like a conditional. Say for example, I'm here decoding like each V packet at, if I'm calling, like I'm defining, okay, let's look at this. Actually, this is an interesting piece of code. Like what happens when you flush a video, for instance, when you have to like flush a video, which means like when you're changing the video, you have to like go through the remaining like packets and stuff that FFmpeg has to, you know, and release them. So what happens here is like I'm looping forever, basically, which what this loop does until I break. And I call vpacket decode, you know, which is like a queue, which gives me a video packet. And I assign that to video vpacket variable, you know, which generates this code here. So
I'm sorry, what are the curly braces, and why are they yellow?
so yeah, these are lambdas. That's a great question, actually.
Okay.
Thank you for. I mean, I haven't. I'm doing like a terrible job explaining the language. This is like very all over the place. But thanks for asking these questions about, like, you know. I mean, these are lambdas, and you know, if you can choose to call them or not. I mean,
Lambdas in the sense that they do they bind any variables, or they're just an invocable thing that leaves an address?
Yeah, it's just an invocable thing that's an address, like, you know, it jumps over
Got it.
between that and, like, I don't like locals. It's everything is global, you know. I mean,
Got it.
unlike
I figured. I just thought I'd ask, because lambda means things to people. Does the and sorry, why I'm confused. Why in that lambda? Why are you using a yellow symbol there? Isn't that doesn't happen at runtime because it's in a lambda, or what's the?
So yellow is also used for, I mean, it's not that much stuff, you know. It's also used for immediate time words. I mean, so that's when you invoke that definition when it's like jitting, you know, and that's like defined outside in the language itself. It's very simple assembly code, you know. It's just like appending that, you know, appending, like what this does is basically say like I want to execute this piece of code. Otherwise, nothing executes, you know. Only the things that are like within this yellow execute, and all of the other ones are like definitions, right? So you know exactly what you're executing if it's like following this yellow bar here. Yeah. So it's either definition or execution.
I see.
And yeah, I mean, you could
got a lot of stuff overloaded on the yellow there. Okay.
Yeah, I mean, I don't know. I like the color, but you can choose
It's a nice
the
color,
color you want. You know, it's. I mean, when the editor is released, you'll be able to. Well, you'll be able to attend like within code. You know, I mean, we can just ditch Zoom and just attend the meeting inside the code editor, right? Like, because you can integrate multiplayer here easily, and also a multiplayer version control system that's like that's scalable to any kind of users. Like Git is not the end all of like version control systems, I think. Like but yeah, we were looking at with Flush here, and like the code, and I mean this calls, this is just a single call, and then this is and then the result of that is stored in Rax, and I move that to vpacket. And then if Rax is 0, I break and I move that to vpacket because FFmpeg requires me to pass it in a pointer. So I have to pass it in a pointer. And 18 is like, what is 18? 18 is a vpacket free, which frees the packet, right? So I mean, I could just
and sorry, how are you actually hooking? You're hooking into to AV codec and FFmpeg and stuff. Like, how is that binding? How are you bridging that divide?
Yeah. Well, I assume that I don't have any floating point arguments, so the C calling convention is like just this. So implement this. So you have to align the SP, which I do by reading SP, like the old stack pointer, into B. Like this is so stupid, having to align the SP, but you have to do it because our operating system requires you to. I don't even use stack pointer like for any data anymore. I just use it as a call stack, and when you think about it, that could have tremendous benefits. You just eliminate a lot of like Stack Overflow, like return oriented programming, like right there, right? It's like this whole program runs without any runtime stacks. It's totally possible to program without having to use any stacks at runtime at all. Yeah. By the way, we could open some demos, maybe. So, yeah, this whole program, I mean, it's not just also CPU side code, right? There is also GPU code, which is like which most other languages, for most other languages, it's an afterthought, right? And in this language, it's so expressive that you can like define the whole SPIR-V like generation in like just this much code, essentially. Like it's not that much. And by the way, even like the fonts are defined in this language. Is my screen showing, by the way, or is it stuck?
Yes.
Oh, okay. It's stuck on my screen, so I wasn't sure.
Yeah, I'd be curious to see that how you define the fonts. It looks like they're kind of a bit of a vector or something, but
yes. So say we're redefining M, for example, to be like so M is here. So I start from bottom left, right, to top left, to center, to top right, to bottom right. So what if I went to bottom center, but I had to switch to the other deck, So yeah. So now it's like, can you see the difference? Maybe can make it. Change the font size here. So yeah, it looks like this now, or I could just make it something entirely different. Denos, like it's just encoding stuff at it's so simple. It's like it's just this much code to it's just all this code is like this much for that language. And yeah, and that's like the font definition, right? I'm gonna undo that. Okay, So and that's like.
Are you hitting something to rebuild the system each time? Is that?
Oh yeah, that's the enter.
Okay.
Whenever I press enter, it rebuilds. You know, you get like very how to say it. You know, you get very used to it. Like 8 milliseconds is so fast. I can't even like wait for C to compile anymore.
Yeah.
But yeah, it also includes all this shader stuff also that I'm defining inside the language. Like
Paul says he can't. Paul, can you see the screen? You were indicating in the chat you couldn't. I can currently see it, but
I can see it also on my other stream.
Okay, never mind.
So yeah, I mean that rendering code looks like this. You know, it's a bunch of shader code, which is not that hard to write actually. You know, and you can do. You know, the cool thing about this language is you can redefine stuff like this, for instance. And there, I just redefined filter. You know, there can be 2 definitions. That's fine. And I can say like, okay, you know, what if I did this instead? Or okay, that didn't change anything. Because what if I didn't do? Okay, I crashed, but I shouldn't. Yeah, it doesn't look on the stream because like the difference is very subtle. Maybe I should look at it more. Oh yeah, I know it. Hold on. There's like the dark modes here. I can show you the dark modes, or how to implement the dark modes. And this is.
I assume that little green dot is your cursor. Is your mouse cursor?
Yes, that's the mouse cursor. Where's the dark modes? I'm looking for a comment that looks like. Oh, there it is. Dark modes. There we go. So it's not exposed yet, but I just enabled dark mode. So I'm gonna open the graphics conference talks, like the you know. And if I close dark mode, it looks like this, for instance, like a lot brighter, you know, versus with the dark mode. So the way that this dark mode works is I've defined, like, I have this floating point constant here, you know, 32 bits, but I have 24 bits currently, so I have to encode it with 2 items on the stack. You know, I swap and shift by 8 and or.
Oh, I was going to clarify. So for compiled numbers, you're just using the 124 bit, the cell with the 24 bits of.
Yes. That means also 24-bit floats, which has precision issues, unfortunately, but you know, whatever, it's fine. It's so yeah, I sample from 4 planes like Y, U, V, and you know, I have defined samplers here as like 0 sampler into sampler Y and 1 sampler into sampler U and sampler V. And you know, the sampler at requires a sampler ID, you know, so because you know, you have to like the sampler handler rather, so you have to set that, and the results, like that samples from that like Y plane, right, the Luma plane, and the UV chroma planes separately. And if the chroma is like, if the Luma is beyond some threshold. Oh wait, hold on. There it is. I'm looking like where? Wait, that's not that code. So if the Luma is beyond some threshold, if the Luma is greater than 0.6, which you had to assign as like condition, you know, in this language, before you call ifs, you had to assign the conditionals to this condition variable. You know, instead of if, you could also call if else, but you have to pass like 2 lambdas.
Oh, okay.
Or
So your conditional is taking lambdas, the thing to invoke conditionally. I see.
yes, and the condition is this variable here that I read into the condition. You know.
And the like GT question, for example, like that's what can you explain what that's taking? Where is it doing the comparison between, and where is it putting its result?
Oh yeah, so the same syntax that we used before, like the dot syntax. So I'm reading from the luma variable, luma dot, and then 0.599f. So in this language, you have to define your floats. So that f does that. And then if luma is greater than 0.6, that generates like this variable, you know, 26e. That's a ID. And that's the condition variable. And then, you know, if that condition is true, this code gets run, which is like inverse the luma essentially. Yeah.
And
But,
sorry,
you know,
the red is reading from the condition variable and then putting it in Rx or DX depending on the.
Oh, the red is storing into the condition variable.
Sorry, storing into the. I see, and then
Yes.
I see, and then if you consumes that.
Yes. It consumes the result of the greater than, which is like generates like a SPIR-V result, and all of that is defined as like, you know, this is just a binary instruction, right? And I read into source and destination, you know, always two stuff, like two items on top of stack. And if I need more than that, then like condition, for example, that's fine, you know, or maybe sampler ID. That's like that's actually better because like you can like define this condition programmatically at compile time if you care to, without having to pass it on stack even, right? Like I mean, the restriction of two stack items is definitely worth it. In the worst case, you just read it. I mean, you just write it into another variable and read it when you have to, which makes also the code a lot more readable. So, so yeah, that's like, you know, a bit about how we can also program shaders in this, and you know.
And sorry, you didn't quite. Maybe I didn't quite follow. So you're targeting Vulkan. How are you actually getting into the formats that Vulkan uses and like?
Yeah, the formats that Vulkan uses, as in
Are you using a what kind of a you're compiling to one of the Vulkan shading languages, or what's the process?
Oh yeah, this is compiling directly into SPIR-V. So
Okay, so you're generating raw SPIR-V bits.
yes,
Got it.
yes. Otherwise, I would depend on another tool, the GLSLine compiler, which is huge. I mean, that's like at least 100 megabytes. I think a lot more than that now with all the debug symbols and so on. And all of that is unnecessary.
Tools are so big now. Yeah, I'm right there with you.
I mean, in C, only like, even though you have all those headers and like for, you know, all those struct definitions, all that convenience stuff that you have in C, it was like I think 150 kilobytes of C code for a much more early prototype version of this idea. And this is now around 256 kilobytes of code, including the shader stuff, like all that font definition shaders, the FFmpeg Vulkan initialization, the UI, and you know, the interaction, the folder iteration stuff, etc. Like, you know, a lot of stuff actually in 200 kilobytes. I mean, the expressivity of Fort is insane at compile time. It's a lot better than, like, you know, the restraints of like runtime fort, right? Which is like, I mean, it has to pass through the stack, and like, question is like, how can it run on the GPU, right? There is like a lot of like expressibility loss just because we want to pass through stack. But that information passing, I mean, you could also achieve that through like global variables. And with that, it becomes much more simpler, faster, and it also becomes, you know, more, how to say, I forgot. It's much more easily debuggable, because like the state is just laid bare, you know. That's just like global state. That's not like you know, you're not trying to juggle like local state space at all. So it becomes a lot more manageable compared to like, you know, all the other languages. So I don't know, what else can I say actually? The Fort stuff, for instance, sorry, the Vulkan stuff is like Vulkan usage is mostly like filling forms, right? So if I look at some Vulkan stuff, like, okay, for instance, I'm creating like images for each for like 420 YUV 420 format. Nice. So the way that I generate this is like 14 info, which is like which fills the information structure. I mean, it selects it and then fills the information structure with the type, and then
what's a dollar? What's a dollar sign?
The dollar sign, that's just a variable.
Okay, you just okay.
It's all cells here. You know, if it's not a string or if it's not a number, then it has to be like a cell, and the tag is like, you know, if it's red, then it's reading into that, you know, whatever it is. There's no single like end-all definition for anything, any of this. You know, it's not going to complain like, oh, this was a definition before, you can't read it.
No, I just wasn't quite following. Like in this context, though, you're writing into it. Why are you writing into it at as you're defining these, and then you're reading out of it after one, like on that lock inc one?
Oh, sure, yeah. So let's see. Let's read this code.
I was up at the top of the block on.
Yes. So if I press enter, we can see like, okay, it's reading 0 mostly, and then dollar is like whatever information ID it is. You know, because in Vulkan you have these. Okay, hold on. You have these Vulkan, say. Oh, my Vulkan is so. Vulkan create info, for instance, or create info. Oh, wait. Types.
You're populating one of the structures that they use. And then...
Yes. So 14 would be image create info, right? So instead of having to type all of that, like we can, you don't have to import that. It's just an ID, right? I mean, these kind of binary interfaces simplify a lot versus like having to, you know, if this was like a string-based interface like OpenXR, that would be awful, right?
It could be worse. It could be goods or something, but
yeah. I mean, in Vulkan, you had to always do this shenanigan where you go like wk image create info equals, and then you copy the structure types, you know, and that's 0. You had to do this for every single time, versus I can just say inf0 for first information, or inf1 for the second one, or inf2, because sometimes you need more than one information structures that are referring to each other, and they're like 256 bytes apart, and you know, they're just a bunch of words. And the last one is info, which is like, okay, if you want any kind of info, like, you know, any kind of offset for this like structure that I defined here as like 8 kilobytes, you know, that's all this is, like 8 kilobytes of globally accessible data from anywhere, essentially. And what I'm saying is like, okay, let's get the info ID, which is mostly 0, right? So, and then add that to that address, and then load that to RDI, which generates this Leah RDI bit here, you know. And then it writes some index, which is like in this case it's 3B9A CDE9, you know, which is like the type information. What is that 3B9A? 3B 9A. Wait, what? That's weird. Oh. That's interesting actually. What am I even writing here? Okay.
You were searching in the header for is it in decimal instead, or
maybe it's in another header. But it should be there. Oh, sorry. Did we lose? Okay, yeah, we didn't lose the screen. Okay, so info.
So actually, when I was asking about the $, I was actually looking up. Can you go back to block 50? I think it was block 54 thereabouts.
Sure.
With the
there we go.
Yeah, so up at the very top, that lock ink bang word. What's going on with the red $ and the green? Like, why are you're reading you're writing into dollars from the and then?
Oh, I mean, yeah, it doesn't have to be. It could be just this.
Oh, okay. Okay, that's just, yeah, I see. Okay. Yeah, I was surprised that you needed. That seemed like an unnecessary step. That was why I was.
yeah, totally. And this
like it seems like you've got a convention for how you're using $ in several of these words. Is that maybe I'm not getting the idiom?
It's just a temporary variable that I really don't care about. You know.
Got it. So you use just your
throw away temporary just for temporary contexts, and you know, sometimes that causes troubles too. Like that happened. If you call like two of those words that are like using those variables at the same time, then you know it could be trouble. But you know, you just define another one. There's so many of them. Like if those, yeah, and it really doesn't matter. Like they're essentially free. I mean, if you were to be like it doesn't cost anything at runtime, so you can have as many variables as you needed. And this is also interesting. So this is compiled, like this is defining memory for runtime, but all that memory is global memory. So I dedicate a single register to be able to access all memory of the program that are stored in this single register, which gives you like gigabytes of state, which is huge. I mean, you shouldn't have to need like gigabytes of space actually. Or you could allocate like, you know, virtual memory if you needed to, instead of like using this global space, which is antithetical to all conventional programming wisdom, which says like, don't use globals. I mean, you know, as if like, if you're like accessing them in a responsible manner, like I can just say like, okay, where am I using upload buffers, for instance, and suddenly it's not that like scary, you know, because like I know exactly where I'm using those, and it's not like, I mean, I'm very critical of Rust's memory safe attitude, where you have to fill tax forms to be able to access a piece of memory, which is just there, like it's free to access, and you don't even have to pass anything on a register to be able to access it. It's just like, it's just there, and somehow, like, you know, people are like, oh, that's unsafe, you know, pass it in a functional context or whatever. So you end up having these like stacks of state, you know, passed through like 20, 30 layers of call stack, like the same state over and over again, which is insane.
So for you're going to target SPIR-V, like I haven't looked deeply. How bad is the encoding? Like, is it's a fairly simple instruction encoding, or what? How bad is SPIR-V?
Sorry, what is encoding for what exactly?
You were going to encode SPIR-V instructions, right?
Oh yeah.
Are they like I don't have a good sense. Are they hard to encode, or is it a fairly straightforward format?
And they're kind of hard to encode, but not really. I mean, you just have to like define it in a you read the SPIR-V spec, which is like SPIR-V, which looks like this. I'm gonna save your eyes. So it defines the whole thing here, the binary encoding and all the instructions. So say like, how would you encode an instruction? Let's see, bit instructions, for example, shift right logical, right? Let's see. Where's shift right logical? Okay, there it is. So 194 binary.
That's not too bad. Oh, so it's just a byte code kind of. Okay.
Yes. I mean, once you have like those words, it's just like 194 binary. I mean,
I don't know how much header and footer and what all you got to wrap around it, but
yeah, I mean, binary is just this one-liner, right?
Okay.
And
Not
vector is just that 4 lines. I mean, it's very simple code, really. Like, and that vector stuff is for when you have, for instance, when you want to shift right 4 item vectors, by
SMD vector or
by one item, just a single. I mean, 4 component vectors by a single component, like float for. I mean, single component integer. Sorry, you can't shift by float, of course.
Got it. Like for I see.
Yeah. And this vec thing is like just that abstraction for that, like reading, like it's just comparing like destination component count with a source component count. And if they're not equal, like, I mean, that state gets written to CX, and this if else works on this condition CX, so that's why it's there. Or like, actually, is that running even? Oh yeah, it's a if else within an if else, of course. So, yeah.
How are you displaying the state when you're on top of a word? Like, how do you have the opportunity to hook that in?
Sorry, how do you mean?
You were showing this. You were showing the state of the stacks of the plate when you're sitting on top of a word. Like what?
Oh,
how do you actually do that injection of the instrumentation or?
Oh, well, the state is just stored in racks and RDX. So if you store that in an array, you can visualize that in reverse order, and you get this.
But I mean, how are you? You're doing that only when that word is getting executed, right? Like, how do you?
Of course.
Are you modifying how you compiled it to have a moment to update this update?
Oh, right. I forgot. I had to look how I implemented it, but I'm probably doing like, code injection where if the cursor is here, like the active cursor, do a code injection where you're recording racks and RDX into this global array that's like storing the state of the stack.
Okay.
That should be it. But I'd have to read the code now.
Okay.
Okay. Which is clear,
Yeah. I was just curious if you had some, but it's all straight line assembly that's coming out. So you're not actually you must be doing something to get in there, right?
Yeah, it's all straightforward assembly, very straightforward assembly. It's just generating the required instructions in JIT, which is compiles to a single call for those white words and a return exchange racks RDX for definitions. And for these, it's just a single jump. And for loads, it's just a single move to racks or RDX. Or for writes, it's again back to the global memory, a single move. It's all very simple.
Like, so how do you keep flaws and bugs from entering your code base? Do you have tests around it, or do you have asserts? I mean, what do you do to try to?
Don't make bugs. That's the Like when you have bugs, what I do is like I triage the bug first by, okay, let's say like I'm triaging why a shader would be crashing, you know, say here. So this shader crashes, I disable this, and does it still crash? Yes, it still crashes, okay. And then I disable this too, does it still crash? No, okay, then it must be in color, you know. Does that make sense? I mean, that's the fastest way that I can, like, there's no reliable way to prevent bugs is like, you know, my experience. You just have to, I mean, there are ways that you can use, like, I've had memory overflows, you know, where I was corrupting memory, and or sometimes I passed the wrong stride or wrong number or whatever. And it's, you learn to discover it at some point. I mean, and you fix it. Trying to prevent it is more effort than it's worth, in my opinion. And a lot of languages try and fail at that because, like, at the end of the day, who's going to prevent logic bugs? You know, there's no compiler that can execute your code for you and tell you, like, oh, you know what? That's not what you meant. I mean, you just have to, you know, write simple code and think simple data transformations to express your code, and most of the time you'll be fine. And if something goes wrong, usually it goes wrong immediately, and you know you can just undo and see, like, okay, you know, as soon as you can replicate the bug, then you just do a triage where you can just undo, or you can just enable disable stuff, and you find the source, like, you know, fast. And sometimes, yeah, sometimes the bugs are like so hard to find, it persists for a while, but they're still fixable. I mean, you just
I've
have
had
to
good experiences with design by contract, which is in the Eiffel language. So you document, you basically you do mathematical things with, okay, what does this code need, the preconditions and the post conditions and the invariants, and then if something's violated, it tells you right away, and then it's a way of injecting integrity into the code, that where the code actually sort of fixes itself in many ways. So I've had good experiences with that, and I was just wondering if anybody else did that. So
I mean, if you wanted to, you could still do that kind of stuff also in this style of programming, right? You could just do checks that are like you express with macros, and you can compress that, whatever you're going to write with this, very efficiently. And if you want to do contracts, sure, go ahead. I mean, this is a metaprogramming language that doesn't impose you anything. I mean, you can say, like, okay, you know what? These are, like, I have, for instance, say, these are my constraints, you know, had to, like, compress that down to 9 characters. So, and you can say, like, okay, you know, the constraint is X should be like this, B should be that, or, like, you know, could be like V0 should be 0, and V1 should be always should be 14, or whatever, you know, like a V2 should be like whatever, less than 64, you know. Like, if this was like your constraint space, you just, like, condensed that, like, constraint, that contract stuff that you were talking about, into Word that you can use where you're, like, you know, using those contracts if you want to. For me, I just
thank you.
I just try to not make that many you know, errors instead, like, and try to maintain the state consistent all the time, instead of, like, relying on, like, you know, checks everywhere. Like, because relying on checks is, like, you know, it's kind of like safe programming. But yeah, I mean, I really like unsafe programming rather than safe programming.
I had a question about the dictionary visualizer on the left. You said that the capacity you've got is for eight characters in the current system. I'm curious why you only show the six characters. Is that just a space constraint, or?
Yeah, space constraint. Like nine. It's actually 9 characters. 9 characters by 7-bit, and there. Yeah, and there are other like encodings also that I've come up with that's not present in this language, which is say 16-bit plus 16-bit plus 16-bit plus 15-bit. So that's like that gives you 64K words, and you can concatenate up to 4 of them together in just 64 bits. Like that should be a much more efficient and much more expressive. And the thing is, you can also, since you have defined all words from concatenation of 4 words, that opens up the possibility of doing, say, like voice recognition in the editor. So you can just bring the words on the screen and say, like, oh, I want, say, instead of having to like say sampler ID, for instance, and then I don't have to go to sampler ID, it just selects it. And which becomes important because it's not going to be keyboard only or desktop only. And also, I also want to port this to phones, tablets, Steam Deck likes, handhelds, VR headsets, everywhere. And even watches or like smart glasses or whatever. Like, and it is portable to everywhere, I think. Just the UX changes, but the code and the whole idea remains simple for all kinds of environments.
I'm also curious how often do you end up using the facility to rename words as you refactor things?
Oh, renaming, right? Yeah. So for instance, non-VG is like non-work groups, but it's like, non-work G, let's say. It's just as simple as that.
I'm curious how often you find yourself using that. It's a neat facility. Like, is it
right? Sometimes, I mean, sometimes I come up with a better, better name. Naming is hard, and you can say like, okay, I'm just gonna name this temporarily, and then come up with a better name later. But yeah, it doesn't happen that often. You're right.
Well, yeah, I was curious because it seems like a neat facility. That I guess on the other hand, like once you're used to a name, you're used to a name. Cool.
Yeah, that's the thing. I mean, it has downsides to compare to text. I mean, text would be contextual, right? So you can just type anywhere. So and with this, you have to bring up like the dictionary that you want, because like otherwise it's a huge search space that you have to search through, like at scale, right? If you build like more and more complex software with this, I mean, you're gonna need more dictionary space, or maybe not even that. I mean, all of this is like how many words? It's not even that many words. I mean, it's just
I noticed you very carefully kind of curated the layout of it. How much do you find yourself fussing with that? That's actually, it's kind of interesting stylistically though, to be that they're laid out in an ordered way.
Oh yeah, that was intentional. So 16 per scroll, 16 words per scroll, which is like this. And so thing is, I'm not really sure about any of this. So this is where it's like, more open to imagination, reimagination perhaps. And the way that I organize those scrolls is like I have tags per scroll. So this is like packs and to do, and I can just go around and say like, what are XAssembly words, which are like the x64 assembly, and these are XAssembly API words, for instance, right? And what are like the SPIR-V words are here, for instance. like this.
Yeah, it's surprisingly organized. Like I think when I've thought of using indexes before, I've always feared that if I just sort of randomly dumped them in the order I created things, it would be disorganized. But this idea of placing them explicitly is pretty cool. That's a really neat idea.
Oh, thanks. Yeah, I mean, organization with indexing is like, the hard part. I thought a lot about this problem. It's I was thinking about 64 verse scrolls, and maybe I will go back to 64 verse scrolls. I mean, it gets a lot of, like, maybe this was too granular. I don't know. All of this is like open to reimagination basically by anyone, because the language doesn't depend on it. The specific editor does, right? So you can have as many editors as you want and code interrupt without having to explicitly say like, okay, this has to be that and that. But if you're like mixing source, I mean, they can interrupt at the source level, but not at the editor level. But that's fine. I mean, I think this language can host any kind of like language, because it offers pure assembly execution, right? There's no blocks there that you have to like go through or that I have to define so that you can do whatever you want. If you can express that logic in assembly, then which is like, which you compile through this macro assembly, right? So it's not like, pure like hardcore assembly that we're used to. It's much more approachable. And yeah, what was I saying? I forgot where I was going with this.
I think I asked a question. I had a different question. I'm curious how you bootstrapped the system.
Oh, right. Bootstrap the system. I mean, it used to be this, and then from that system, I mean, it still uses C, unfortunately, but the next version is going to be standalone and entirely self bootstrapped. So this compiles into assembly, and I host that in a C project to make this editor, which compiles, WAMP and all the other stuff. And the next version is going to be also programmed in this, and like we're going to program it live basically, all of it, so that it can be something that can be like passed on from generation to generation, like as foundational bootstrapping knowledge, like, okay, this is how you can build this editor if you had to. It's so simple, and language is much simpler than the editor, of course. Like all the complexity is just editor, and other than that, like yeah, the font rendering. But you can also have the editor stand alone, which means like if you want to embed the editor to say into a game, you can have the game have its own text rendering and just expose the editor and its interaction and so on. So yeah, I mean, I expect a ton of editors for this programming language for sure. Like, hopefully. I mean, if people find it interesting. So what else I can say, like, about...
So what have you built games or like what are the things that you build with this?
So I built, before VAMP, I built this... I'm going to go back and... Wait, did I open the tab there? No. Sorry. So I built those biological stuff that's going to ship also in WAMP. So this was also done in the previous iteration, so which looks like this. Okay. Wait, hold on. All right. Okay. So, yeah, it's like this galaxy-like structure that expands. It's just a shader. Unfortunately, it's running a bit slow because I'm trying to stream it at the same time. So sorry about that. Maybe I can open up. And other than that, the editor itself is so. This was the previous version, and you can see I don't know if you can read the text, but I was still opening and closing definitions back then. So there's that. And if I change this to something much more dynamic, so that we don't have to wait so much. Oh, okay, let's get this. So yeah, is that, yeah. So you can use this philosophy for any kind of coding, I think. It's what you can do with this is boundless. You just think about what's the code that I want to generate and what's the logic that's required to generate that code. That's all that's required. That's all this is. All the rest is just implementation details. I mean, you could still have a stack larger than 2. It's going to run slower because you have to manage all that stack back and forth all the time. Versus you could have it in global memory, which works a lot better in my opinion. Just do exact opposite of programming knowledge, and you'll do fine, basically. Don't do locals, or don't do I mean, you can still do locals if you had to, but yeah, I just like passing stuff globally instead of having to re-access the same context locally all the time. And programming assembly gives you a lot of freedom. So compared to so that's the new stuff, and that's the older stuff, basically. So assembly is essentially much more freeform than dealing with compilers. So SPIR-V is dealing with compilers, right? So I have to be explicit about everything. I have to read stuff into variables, and I have to, if I have to use a result, there is no implicit place I can go for that result. Versus in assembly, all the registers are passed all the time. So you don't have to pass stuff on the stack. It's implicitly passed for you by the processor for free, right? So that's the major difference between assembler and compiler. Apart from the whole complexity difference, there is also a lot of implicitness intrinsic to the assembly language for, I mean, I target x64. You could target another architecture. Ultimately, it depends on where you're going to run this code. I highly doubt that I'm going to run the same code on a Commodore 64, on a 6502, or but if I had to, I could totally emulate it. It's just going to be slower than having programming directly to the specific architecture. But you can do binary retargeting, or in this case, execution retargeting, because you haven't produced the binary yet. You can execute logic before you produce the binary, instead of having to translate back from binary. And so yeah, there is that implicitness about assembly, and it makes stuff a lot less code than if you had to write everything with a compiler where you had to pass all the values explicitly instead of in assembly. I can just say cursor at B and then bx greater than. Oh, I know that I read bx here. I didn't have to pass it. I didn't have to define a new variable. It's just bx. I mean, and that generates just a compare and a jump. It's all super efficient. Yeah, I mean, let me look at my notes to see if we missed something. I think we got to the most important stuff anyway. Do we have questions, comments, you know?
It's a really neat system. A lot of cool ideas, a lot of stuff that it's very thought provoking.
Thank you. Thank you. Oh, I just thought something that we didn't get to was conditionals, right? How do you conditionals with the block, like basic
Yeah,
block?
I love the look of it. It's a really cool system. And I like
Thank
how
you.
responsive it is.
Thank you. I mean, it's I didn't actual motivation was I wanted like a system that looked super cool when I was you know, dropping acid basically. I mean, like it had to be simple enough. It had to be like, you know, it had to also look cool, and this is gonna look even cooler than this. I mean, this is like the font here. It looks like, you know, you can get many different looks with this style of, like, you know, font design. Or my favorite look is like this. There you go. Yeah, kind of like. And okay, how do we do conditionals? So the conditionals work within basic blocks, and so you can open up a basic block, and it will constrain the assembly output to that basic block. So, for instance, here I'm loading the temporary address, which is just this tab mem Leah, to rags, and then I'm reading that into R11. And if I didn't have this, then the assembly output would get like very I mean, like it's nice, you know, because you can see within a single basic block what's the generated assembly for this basic block, right? And within a basic block, as soon as you do a conditional, if that conditional passes, then the block continues, you know. So let's see. For instance, if okay, let's find a conditional. It's like okay. Okay, yeah, let's go back here. So if the packet is not 0, then I free that packet, you know. If there was like more conditionals after this, you know, I see that if the focus video is not 0, then I execute this rest of the code until I encounter this here, which is the link, you know, which is the else part. So instead of else's, I have these, you know, links here that are like all across the code, actually. That can be also used for C calls, can be used for conditionals. They can be overridden. You know, hold on. I'm going to try to find like a conditional. Most of the time it's used for C calls, which confuses right now. But yeah, so right here, for example, I'm saying like, if I'm full screen, I'm not going to do anything, and if I'm not full screen, I'm going to call this function called UI tally, and then I'm going to call setup, which sets the slot ID to 0, and then slot live count to 0, and then it iterates through all the slots, and then it does a check, you know, and the check is like, if this is live, you know, if this slot is live, you increment the slot's live count by 1, and then if this slot is a leaf, you know, so you keep filtering. So if this is live, then it's past this filter, you know, and then you check for leaf, and you know, if it's also leaf, then I check, I decode the bounds. You know, I get the bounds of the slot and then I decode it, which you know, reads it into local variables, and then I do a hot check, which is like doing like a mouse check for between the mouse and the slot bounds. You know, and if it's hot, then the hot slot index is the slot ID, which I passed implicitly, by the way. This is R12D, you know, this R12 passed implicitly. I didn't have to define the slot index for this function. It's just there. It's global, and this hot slot is also global. So you don't have to define these, you know, arguments all the time. You can just, you know, use stuff anywhere, use memory, any memory anywhere, basically. And so yeah, I set the hot slot, and then I get the video of the slot, and then I set it as a hot bit, and then I return 1 in A or 0 if it was not hot, you know. So yeah, it basically checks all the slots if I'm not full screen. And so I can get the hot slot index, which gives me like what my mouse is hovering, right? So I can do stuff with it, but I don't have to pass that like everywhere in code, you know, all the time. It's just free. I mean, it's a lot faster and simpler to pass it globally, unlike, you know, what everybody else does. You know, C, Rust, yeah. So yeah, that's basically how I do conditionals, and how I pass state around. I mean, like using state everywhere I can, you know. And yes, you have to care about lifetimes. If you modify the same state from like multiple threads, you're going to have troubles, especially on like platforms where you have to synchronize that access. But, you know, I care about lifetimes. I'm just accessing this data from a single thread. There cannot be like a race condition, because like I'm not writing it from 2 threads. Like reads from multiple threads is fine, but as soon as it's writes from multiple threads, then you have to use like locks and, you know, stuff like that. You know, locks as in just this keyword called lock. I mean, wait, what? Where's lock? Oh, I'm looking at. I still have the SPIR-V. Yeah, so lock is just a single byte on x64, and you can use it on a bunch of instructions, including bit test reset. So if you have to set or reset like a single bit from multiple threads, then yeah, that's totally possible. I mean, in C, you would have to like ask the compiler specifically to generate it or use like intrinsics. Yeah, I like being able to just say like, oh, not this. Sorry. I like being able to just say like lock, just being able to append, like, you know, if I append this, then it becomes a lock add, you know. If I don't call that, then it's just a single add. So yeah, it's very powerful, but you're responsible for all the code generated. You know, you can still use compilers like in SPIR-V, but yeah, I prefer to use assemblers because I like the full control and the freedom that assembly gives instead of like compilers and explicit parameter passing. So yeah, that was a lot of stuff. Let me check my notes if we missed anything. So I have like a word here called stack fetishism, which we didn't get to. Like I just don't use any stack juggling words except for swap, which you need, right?
So you're releasing it tomorrow? Is that what you said?
Not tomorrow. I'm gonna start a live stream where we build live on live stream, and then we're gonna release it after we're building it on live stream. You know, because it's not like I just need one last iteration. But I can maybe release it earlier than like it's gonna take 1 month, I think, to recode this live. Maybe a lot less than that. I don't know. We'll see. Not too long. And the application itself is, yeah, right now I'm waiting for Steam to review it. But yeah. The thing is, there are like, this is not the final form also. This is the 24-bit version, but it's going to be 32 bits plus 8 bits for tags and, stuff. So yeah, it wasn't the final form. Like this was, I knew that this wouldn't be the final form, and like, because this was my first binary attempt. Before this, I had like 2 other text forms, and this was the first like binary form, and I thought 24 bits would be enough, but in the end, it's slower than using 32 bits. And the reason for that is if you have tags together side by side, like compact on an array, single byte tags, then you get fast skips, So empty blocks you can skip super fast by just reading eight tags at a time and check for 0. Like read 8 bytes and check for 0, and if it's 0, then you can skip it. There are no instructions there, versus you had to read 32 bytes and do like 8 compares to see at least if this was like a comment or not, basically. Because tag 0 is essentially comments. Yeah.
Cool. Well, that was really awesome.
Thank you.
All right. Well, I think that concludes our meeting. I'm going to hit the stop button on the recording and see you all next month.